Everyone, welcome to the lecture series of Advanced Structural Analysis. The next topic is the influence line diagram. Now, in this class, we will discuss about the ILD, which is influence line diagram for the determinate beam as an overview. Then we go on to the influence line diagram for the indeterminate beams. So as we know, the influence line diagram is drawn for the beams when a moving load, a load of a truck load moving over a bridge carrying the wheel load as a point load. So the response quantity due to this wheel load is to be determined. The response quantity could be one is a reactions, shear force, or bending moment, or deflection, or stresses, and so on. For a similar supported beam here, so next example, you can see the truck, and the distance between each of the wheel is also to be considered, so that the moving load with a certain distance can cause the maximum bending moment or maximum shear force at a particular section. Similarly, in the third diagram here, the bridge, the arch bridge, and a train moving over that. So we can know the load from each of the wheels, and the distance between each of the load is fixed and known, and we can find out the maximum bending moment or maximum shear force or maximum deflection due to these loads when the train of load is within the bridge, or some portion is across the bridge, some portion is on the bridge, and different load conditions we can find out the response quantities. So now, as an introduction, we would like to go for the influence line diagram for a determinate beam. For example, I would like to take a simply supported beam and this will be a roller, and now due to a unit load, so by definition the influence line is a curved line for the unit load when the unit load moving from one support to the next support. So now, if this is the case, so let us see the influence line diagram for reaction. So I can draw influence line for reactions. So here we can have two reactions, which is RA and RB. So if I try to draw a influence line diagram for the reaction here, so I can draw this line like this, and for a point load on this beam, so I can try to see, and for this load try to take a moment at A and find out RA and find RB, and then we'll see that the influence line diagram is something like this for RA. So this is ILD for RA. This quantity will be maximum 1. Similarly, the ILD for RB will be here and goes something like this. So this quantity is 1 unit. That means when unit load is at B, so I will get a maximum reaction of RB which is equal to 1. And as the load goes aside, RB goes on reducing. When unit load is at A, the RB value will be 0, which is obvious because entire load is in RA. So this is the ILD for reaction at A and B. Similarly, we can try to find out the ILD for cantilever beam. Suppose this is the cantilever beam. So let us say I have a unit load here, and this is a point A and point B. I am looking for, let us say, reaction at A. So if by moving the load 1, reaction, the entire load should be taken by support A. That means irrespective of your location of 1, the reaction remains unity. That means throughout the beam, moving of unit load throughout the beam, the reaction remains 1. So that means this will be my ILD for RA. Quantity is 1. So this is the ILD for RA for a cantilever beam. Now we can also write down the ILD for the shear force, ILD for shear force and bending moment for a simply supported beam. So let us see, if I have to draw a shear force at a section, shear force and bending moment will be at a section. So let us say I will take a section at a simple supported beam, that is a point section C. So at that point I will have to draw something, a shear quantity, right? Something like this, the shear force applied. So then obviously beam goes something like this. Means a unit shear has to be applied at the section where we want to find the shear force. Then joining this unit with the B point and A point, so this becomes my shear force at section C. So this total quantity will be 1, and this quantity will be, this one quantity will be equal to, the down one is, suppose this section is a distance of A and this section is distance of B. So this will be my A by L, this will be B by L. So this ordinate will be B by L, assuming that entire length of the span is your L. Similarly, if I am looking for a bending moment at a section C, simply I can see a unit load moving from point A to C at a distance, let us say x, right? Then finding the RA and RB, so movement at C will be mx mxb by L. So nx is equal to 0 to A. So W, which is unit load 1, so AB by L. So this quantity will be AB by L. And similarly, when unit load is taken between B to C, so I'll get again X varying from B goes up to here, up to the section, maybe B. So again I'll get AB by L. So joining this ordinate to this ordinate, so this ordinate of the bending moment will be equal to AB by L. So this is the shear force and bending moment for simply supported beam. Very simple. If you want to find out the ILD for shear force in a beam at a section X, let us say this is a section, let us say X. I want to find out shear force at this section. So you take a point load, let's say 1. When a section unit load 1 moving from A to X, the shear force at this point will be 0. When the unit load moving from X to B, then there is a shear force only up to the point. So that means the shear force up to the when unit load is moving from A to X, no shear force. And then when unit load moving from section X to B, then we have a shear force quantity. So this will be the shear force quantity, shear force for the cantilever beam at section X. Now you may ask, how do you find out the total bending moment, total shear force for the simply supported beam? Then simply, suppose the question is given, so I have a simply supported beam. I have a 2-point load which is 2 kilonewton and 5 kilonewton, and a distance of 2 meter, and this is a distance of 2 meter, and total span is, let us say, 8 meter. If it is asked, find shear force at section at let us say 4 meter from left support. So what we do, simply we draw the shear force diagram at a section 4 meter. This is a shear force diagram, ILD for shear force, which is, in this case, A becomes, the A will become 4, L is your 8, so A by A, this also becomes B, so half, this is a 0.5, this also will be 0.5. Now simply, you transfer the load, so this is minus, this is plus, so transfer this load, which is 2 meter from here, somewhere here, another load is here, fine here. So this will have 0 influence, because at that point shear force will be nullified. So only this ordinate multiplied by 2 kilonewton, right? So now this is a 0.5 and this distance is 2 meter. So we need to work out this ordinate, let us say y. So y by 0.5 is equal to 2 by total distance is your 4. So y equal to 0.5 times half, which is 0.25. So then the shear force is equal to 2 into 0.25, which is 0.5 kilonewton. So this is the shear force, which is negative value. So that is the shear force at a section 4 meter from the left support. Similarly, if it is asked find bending moment due to these loads at section 4 meter, so find bending moment, let us say at x equal to or at a distance of 3 meter from left support. So what we do, simply for the beam, given beam, two kilonewton, this is 5 kilonewton, and total length is 8 meter. At a distance of, this is 2 meter, and this is also 2 meter. So I need a bending moment at a 3 meter from the left support, means somewhere here. So I will draw ILD for bending at that. So this ordinate will be AB by L. A is my 3 meter, B is 5 meter, my total length is 8. So this will be 15 by 8, maybe point 15 by 8, 1.9 something. And now transfer these loads directly here, and using the similar triangle concept, just find out this ordinate, let us say y1, and also find out this ordinate, let us say y2. So y1 into 2 kilonewton plus y2 into 5 kilonewton will be the total bending moment at section, let us say x. This is x. If the load is UDL load, something like this, if I want at a section x bending moment, so simply I need to take the area of the ILD between the loads. So I just transfer here. So take area covered by the load. So I know this ordinate because from the similar triangle, this will be your AB by L. So using similar triangle concept, I can find out this. Again, for this also I will find out this. Then I will be able to get the area, and that becomes my bending moment at the section X. So this, as far as determinate beam is concerned. And there are different methods to find out this. Simply we use only the equilibrium conditions. So in order to find out the ILD for indeterminate beams, we have conjugate beam method, we have Muller-Breslau law principle. We can find out the ILD for prop cantilever, fixed beam, continuous beam, for the reactions, shear force, bending moment at a given section. So let us find out this response quantity for the indeterminate beams using Muller-Breslau principle in the next class. For now, thank you so much.